Hello everyone. Today we're going to go over how to connect the Artix-7 FPGA to an analog-to-digital converter. And if you've been following along this playlist, we've gone over fixed point arithmetic, how to multiply, add, and divide in hardware. We've gone over how to use the BCD module in a 7-segment controller to display the results of our fixed point modules on the 7 segments. We've learned about UART, how to transmit information to and from a computer, and there's many more things that we're going to get into, but now we're going to start with a very empowering thing. That's what this video is going to be on. And knowing how to hook up an FPGA to an analog-to-digital converter, it's not at all easy for someone just starting out, but once you learn how to do it and to do it right, it becomes very, very empowering, because then you're going to be able to do all sorts of signal processing that you want to do. And if you're not someone if you're new, like if you're not someone who's been watching this playlist in order, but yet you've shown up to this video, I encourage you to find the start of the playlist and watch from the beginning. It's a good playlist. And also, if you're a repeating watcher and you want to support the channel, feel free to buy my book. One of my books, this playlist is describing all of the lessons in this book. If you're already watching, that's good enough, but you'll get everything you need. But if you want to support the channel, feel free to buy that. I'll post the link in the description. Not required, but it'll definitely help out, especially if you're passionate about this and you feel this helps and you want to give thanks. But anyway, let's get started now. So the analog to digital converter that we're going to hook up is the ADS7816. This analog to digital converter is a 12-bit converter, and it can sample at 200 kilohertz, and it's primarily used to convert voltages that are between 0 to 5 volts. So so this is the data sheet, and in this lesson, one important skill that I'm going to try and expose you to and hopefully teach to a good level is how to interpret these data sheets, because unfortunately, the data sheets are not written in a simple to understand way. But we'll go through how to extract the information that is needed from this to then design a controller in Verilog to interface with the actual chip. So yeah, let's go down to the main part. So here, this is the main part. Like, you see that there's two main parts. There's this part, and then there's this part right here. The pinout, that's important, but then also knowing what signals need to be driven by the FPGA. So VREF and VCC, that's just going to be connected to power. VN and V minus, that's the positive and negative end of your analog voltage that you want to convert. Ground is just ground, so ground and negative in get connected together. And so yeah, pins 1, 2, 3, 4, and 8, those are all just connected, not even to the FPGA. The only things that the FPGA is connected to is pins 7, 6, and 5. Those 3 pins. And yeah. So here, there's two modes, but only the mode at the top is the one that really matters. So to initiate a communication, the chip select needs to be driven low. Then the D clock needs to be driven. So the FPGA is going to drive the chip select and the D clock. And then the chip, once it's been connected properly, is going to shift out the data. And the FPGA will use its D clock to sample that data on the rising edge. So the FPGA is both driving that clock and using knowing to sample D out on the rising edge of the clock, starting at B11. So now we're gonna go here, and we're gonna explain. So we're gonna explain the whole process of knowing how to design a controller. So anytime you want to design a controller in Verilog for a specific chip or camera or any device, you need to understand how it works. And that datasheet, unfortunately, did not efficiently articulate how it works. But this waveform here explains everything flawlessly. So there's 3 signals. The FPGA needs to drive chip select. Oh, and chip select is normally high. So it starts off as 1, gets driven low to initiate a communication. And the FPGA will only drive the D clocks only after 30 nanoseconds have elapsed. So this time from this edge to this edge, that's called T sucks, I guess. That's what the datasheet called it. That needs to be greater than 30 nanoseconds. And then once you've done that, the period of the clock, this D clock, it needs to be greater than or equal to 300 nanoseconds. And then the overall time from, and then at the very end here, on the falling edge of your last clock, the chip select gets driven high. And also after that, it's not shown here, but that's when you emit your output, because the chip is connected to the analog voltage, and it's going to convert that analog voltage into a 12-bit number that represents the analog value. So the D out, the chip will serially send the 12-bit result, and by the end here, we'll have the 12-bit number corresponding to it. So yeah. But anyway, so on the datasheet on page 8, the way we extracted this information here was through this sentence there. It's really buried in there, but the only way you can know this is to find this sentence. So yeah, zoom in on that. So the duty cycle of the clock is essentially unimportant as long as the minimum and high load times are at least 150 nanoseconds. So this needs to be at least 150 nanoseconds. This needs to be at least 150 nanoseconds. So the overall thing combined gives you a period of 300 nanoseconds. And then here, this is where we get our information about the other 2 parameters. So TSUCS, that value here, fortunately they actually tell us that it's minimum 30 nanoseconds. Here, it's a little bit more ambiguous, unfortunately. They don't just tell us that it has to be 5 microseconds. They made the low IQ decision of just saying it's 200 kilohertz. So then you have to take the kilohertz and then convert it by dividing 1 over 200 kilohertz to then know that T-psych is actually 5 microseconds. But from that, you're able to extract the needed information. And then you might look at this and think, oh, well, the chip select, it's just a pulse. But in reality, that would trip you up, because it's not just a pulse. It's actually normally high. It's high between transfers. So it looks like a pulse here, but in reality, it's just going to start off as high. So from here, this is how you know that it's always starting off as high and will always be high until another transition starts. So, and then this here is how the chip is connected. We have our VREF and our VCC connected to 5 volts. We have our analog voltage source connected here and here, negative in there, positive in there. Then we've got our grounds connected to that. And then we have our 3 pins connected to the FPGA. So this is how, so this here is how you connect the chip, and this is how you know to interpret the design here that I've got at the top. So yeah. So the first step is going to be to make a Verilog module that receives a start pulse and then drives these 2 signals, processes the D out as an input, generates a 12-bit value at the end, and asserts a done pulse. That's going to be the first step. That'll be our overall analog-to-digital controller IP block that we will make for this specific chip. Then using that, we can make a top-level module to continuously sample. And in this video, I'm going to actually introduce a new tool called the ILA, where we're gonna actually monitor the signals in real time. It's going to be very empowering, so it's very important that you stick around for that. Okay. But anyway, so we'll just use this project. Let me get my current code for the controller, and then we'll explain how it was derived. Let's exit out of this one. Okay. So the code for this is actually quite short, just 80 something lines. Could be even shorter if we chose to make it be shorter. So let's start. So we have our clock input, then we're gonna have our start pulse. It's just gonna be a single clock cycle pulse that comes in to then let the module know when to start emitting this pattern, while simultaneously meeting these 3 timing conditions. So then these are those 3 signals, the 2 outputs and the 1 input. These 3. Then those are the outputs of the converted result. So obviously we're going to need a counter. Then we're going to need a state. And then we're going to need to keep track of how many pulses are going on. And then we're going to need to internally keep track of all 8 bytes. Then we're going to set some parameters. Then we're going to initialize everything, all registers. And remember, chip select gets initialized to 1. Okay, so that is 32 lines of this. Now let's explain the remaining 50. So state 0, we need a state that just does nothing. Nothing happens. So state 0, it'll only go to state 1 where things will start happening if the start pulse is received. So once that's received, we're going to continuously count. And then once the count is equal to delay 1 here, the chip select gets driven to 0. And we go to state 2. So what that does is it makes it be so that once we get into state 1, we keeps the chip select high for a time that is equal to delay 1, and then go low while transitioning into state 2. So right here, actually, let's say our start pulse gets received here. We're going to delay for a little bit. Then once the count is equal to delay 2, we transition into state 2 right here. Then, once we're in state 2, we need to delay again, because remember there's T, S, U, C, S. So we delay for a time that is delay 2, which is just 3 clock cycles. Or it might end up being 4, but it's a small number. So we delay for a small number, 30 or 40 microseconds. Nanoseconds. And then after that we go into, so once we get into state 3, it's going to happen somewhere like right here. The count is equal to 0, but so then we're going to continuously count up. We're going to continuously count up. Yeah, we're going to continuously count up. Then if the count is equal to delay 3 over 2, we drive the D clock to 1. So after D over 2 units of time, we drive it to 1. Then once D2 more units of time have happened, once we get here, we drive the D clock back down to 0. We reset the count back to 0. And we increment the clock count because we will have finished driving our first negative and positive part of the first clock cycle. And then we store the internal result of it. Okay. And we repeat that process until we get to the final one, where then we go to state 4. Once we're in state 4, we already drove our result during the transition, so then we need to make the down pulse go high, and then we make the down pulse go low, and then we go back to state 0 and wait for it to start again. So yeah, that is how the code works. So now let's run the simulation. Okay. So this is the simulation of what's going on. This will explain how this relates to the code to make it simpler. So the chip select is going to be normally high. Once our start pulse gets in, we go to state 1, and when in state 1, we stay there for delay 1 amount of time. So go back to our test bench. So delay 1 was 10. So we stay for 10 clock cycles worth. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Well, it's 11 because it's 1 plus in reality. But that's just how it works out. So then once we've delayed for that much, we go into state 2, where we delay for the minimum time TSUCK, which is 3. So 1, 2, 3, 4. Like, if we wanted it to actually be 3, we would just do this, like -1. Oh, I didn't think I know what it was. It was the order of operations. Yeah, we need to have parentheses here. Let's just put parentheses there just to keep that one safe. Okay. Yeah, now it'll work. Okay. Yeah, let's go through it now. So, yeah, now I know what's going on. So initially, the chip select is high. Get our start pulse. We immediately transition into state 1. Then in state 1, we delay for that amount of time. Since that's 10, that corresponds to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 clock pulses. Then for delay 2, we go into state 2, where we delay again for delay 2 clock pulses. 1, 2, 3. That's that. That's TSUCK. I mean T sucks is what it was called in the datasheet. So technically we can start asserting our clock there, but the way I have it is we go into state 3, where we delay for half of this one. So this was 30, so that means we're going to delay for 15 before we assert the D clock. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah. 1. So yeah, that's 15. And then we keep counting, and once we do it for 15 more, if the clock count is not 14, we reset these two back to 0. We increment the clock count, and we store the internal result. And if you notice, the clock count keeps track of each thing, but we're only concerned about the ones after 2. So we can't store clock count index 0 anywhere. We got to store it starting from here. So that's why we get this weird thing inside. And then if it's 14, it ends. So that's how that works. So now, let's say we wanted, now that we know how it works individually, we can go on to make a top level module for it. Oh, and it's important to note that in the code that's going to be provided in the description, I'm not going to have the -1 for each parameter. It's just going to be how it was before. And it's actually better that way, because you don't want to push it too close to the maximum you don't want to get too close to the fastest allowed converting speed, because we're already getting close. So like, let me pull up the thing. The bigger T-psych is, the bigger the period is, the bigger all of those are, the more guaranteed the chip is to work. But the closer we get to these values, the more likely it is to fail, because then we're pushing the edge of what the chip can do. So we're already close enough. Having it how it is good. No need to go faster. So that's why I'm going to use the one in the description will be the slightly more redundant one, where we wait more than what we need to, because it's just safer. Okay. Yeah, let's go to our top. Source file. Test bench. And this constraint file is already there. So, okay, before we generate the bit stream, I'm going to explain how this works now. So, to make it continuously repeat, all we need to do is make a top level module where we instantiate the controller we just made. This controller takes a start pulse and then does one measurement at a time. Then what we do is we just make an automatic pulse generator that just drives the start pulse again and again. Makes a pulse every six microseconds. So that's what this simple module is. That's all it is. It just generates a pulse every 6 microseconds. So by interconnecting them like this, we're able to continuously sample and continuously update the result in done. Then we have an ILA here so we can monitor all the signals in real time. Let's go through how that worked. So here, so that's how you do it from scratch, but we already have one. Yeah, this is how we configure it. So we have 6 ports. We want to sample for as much time as possible, so I select this one. And we have a bunch of 1-bit signals, but one 12-bit signal. So that's just that. Those are the settings of that. And yeah, so now let's generate the bit stream. Now we can go to program the device. And before we do that, let's revisit how this works. So to make the ILA from scratch, you would normally click this, then you click OK to everything, and then you would say yes to generate instantiation template. And then what you do is, hold on. Then you would go to IP sources, then you would go here, and then this is where you would get your instantiation template that you would then copy into your source file, and then replace these names with your signals and your clock. Okay, but anyway, now that that's been taken care of, let's open up our target. Okay, so this is our ILA, and let's pretend all of this just wasn't here. So we need a signal to trigger off of. So we're going to click our start. Say when it's 1. This is just a pulse. Then we're going to need our signals. Click OK. Then So then let me get my thing. So we have our function generator and our power supply. Got a power supply there, function generator there, which is making a simple sine wave. And we've got our chip hooked up. So whoa, infinity. Oh, my thumb hurts. Okay. Okay, so let's get this out of here. So now that you see that it's all hooked up and the analog signal is being injected, now we can trigger on the start pulse. So we have our start selected. So when I click this button here, so yeah, it triggered. Let's change this radix. So yeah, normally it would be like this. So this chip select, OB, OBUF, declock, OBUF, all of these things, this is not a test bench. These are the actual signals in real time that have been captured with the internal logic analyzer unit. So when we set up that thing and instantiate this, we get our own logic analyzer to then debug in real time. So that's what this is. So we have our chip select, it's going low. Oh, we got our start pulse. So when it's doing exactly what we want. So when the start pulse comes, the chip select remains high for a little bit, goes low for a little bit. Then it, oh, when did I do that? It goes low for a little bit. Then we drive our declock before driving high. And then the entire time we're sampling what's on the D out, and then at the very end we drive it. So we get all these values continuously coming in through our result. But if we change the radix to unsigned decimal, and then we change the waveform style from digital to analog, we can see that the actual sine wave, where is it? So yeah, we can see that the actual sine wave from our signal is being captured perfectly in real time. So do it again. Perfect. So let's say we want to change. Whoa. Like, let's say we want to make it be not a sine wave, but I change it. Then we make it be a square wave on this. How do I do that? Oh. Let's say we want to make it be this. Okay, so now it's emitting that. So because we just changed it to make it be a triangle wave is now the analog signal there. So the FPGA is going to detect that. So now, yeah. Now I'm going to click on the trigger. And there we go. We have our triangle wave that was detected. And let's see, we want to increase the frequency. Frequency. Make it be faster. So 50. So now let's do it again. I guess that was too fast because this thing can only sample so quickly. Go to 20. Yeah, that's kind of towards the limit of what it can do, I guess. What if I change the wave type? Can it do a 20 hertz sine wave? Let's see that. I mean 20,000 hertz. Okay, it can kind of do it. Hold on. Oh yeah, go into analog settings. Hold. Okay, that makes it a lot more clear. So now we can see every unit of time that it samples. Because remember, each thing that goes on from here to here, it can only update its value at the end of each one of these cycles. So it's doing a good job, but we need a much faster analog to digital converter to be able to sample the higher frequencies. And that's by no fault of our own. Our code is completely correct. This is just what the limit of what you can do with this specific chip. But you can do a lot with this. This is a pretty high frequency. That's pretty high up. Let's go. Let's go to a nice safe 10 kilohertz. So we're at 10 kilohertz now. Yeah, much nicer. And let's lower it even more. So we'll go to 5 kilohertz. Let's see how that goes. Oh yeah, very, very nice. So yeah, it can sample lower frequencies flawlessly, but once we get to too high of a frequency, the ADC hits its limit of what it can do. So yeah, so that is how you use the analog to digital converter chip that we have discussed. And you can use the controller to, like, if you go out and buy that chip for like $10, you can use the code here. It's all provided in the description to very quickly incorporate the analog to digital conversion in your own projects whenever you want that. So, but ideally you would understand this whole process enough to the point where you can get a different chip, different data sheet, understand how to come up with understand how the chip works, and then make a controller for it, all from scratch, optimized for that specific chip. Ideally, you know that, but if you couldn't get that, on the bright side, at least you have a very high-performing system for your own hobbyist experiments. Okay, and in the next video, we're going to implement a digital filter using Xilinx. So we're going to feed this converted result into a filter where we're going to filter out the higher frequencies. So then only lower frequency signals can pass through. So that's going to be a very interesting thing that we're going to do next video. So yeah. All right.